So the last section of this module 1 is, of course, examples. So we're going to go through some examples to justify and apply the learned series in previous slides to see how they really work. I call example 1, 2 as warm-up examples. And to the rest of examples, I suggest all of you to pause the video and try yourself to see what kind of trouble you could have and confirm your solutions with the key. Okay, let's start with example 1 here. It's about a very practical battery charging issue. Feel free to pause the video to read through the problem, and here I'm just go ahead to present the solution. My solution will be presented under a doc-cam. Hopefully it's clear and organized enough. If any problem, just bring it up in the office hour or via email. Anyway, example 1. What we are seeing here is actually, it is mentioning 1000 milliampere hour. I believe the first thing we have to figure out is milliampere hour is talking about what? Remember in the video I ever mentioned the unit of a quantity is not only telling you the magnitude or size, but also telling you what this quantity is. So here is a very typical example for that. And so milliampere hour is the unit of what? Without knowing this, we can't proceed. Okay, and the answer is the unit of charge. How could that be? It's because of this equation we learned. Okay, the current is equals to the rate of change of charge. So you can tell the charge could be equal to the current times a certain amount of time. Therefore, the charge unit could be the current unit, which is ampere, times the time unit, which is second. So obviously here is using milliampere and hour, so they're pretty much making sense. So 1000 milliampere hour is talking about the charge of the battery. So with this amount of current, how much time means nothing but dt requires to charge this amount of charge. How much charge we need to charge? Well, it's a little bit twisting, but hopefully you know what I mean. So fully charged means 1000 milliampere hour. Empty is meaning 0 milliampere hour. So the difference between them is the dq, is the total amount of charge you need to charge. The total amount of charge divided by total amount of time spent is equals to the current. And now the current is given as 250 milliampere. The total amount of charge you need to charge is 1000. So denominator dt is the time spent equals to this, the ratio between dq and I. Turned out to be 4 hours. Is the time you have to use to charge fully. After fully charged, of course, immediately the battery has 1000 milliampere hour charge stored. No problem for that. It's not necessary, however, if you want, you can do a conversion from this unit to SI. So 1000 milliampere hour equals to 1 ampere hour, and also equals to pretty much 3600 ampere second, right? And ampere second is SI for charge. In other words, 1 ampere second is equal to 1 coulomb. So end up with 3600 coulomb. Okay, be feeling much better about this coulomb unit, I believe. And the question B is asking for how much charge left. So following the same idea, so fully charged 1000 minus 200 milliampere current times this amount of hour, and then end up with 200 milliampere hour charge left, and convert it to column, which is 720 column charge left. And to example 2, we have up to 5 elements in the circuit and looking for the power of 5. And also looking for the voltage across it. How to do this problem. Again, feel free to pause the video. And so obviously, by reading the problem, you need to first understand this is a example for so-called power conservation. Now, what does it mean by power conservation? It means the total power in the network, in a complete network, should be 0. How to think about this? You can think in this way, that the power provided by something equals to the power consumed by others, right? So if you count in the providing and consuming into the sign of the power, then the summation of them total is equals to 0. For this particular example, we have 5 elements, so sum their power together, we should end up with 0. And by reading the problem further, we should come up with these 4 results. Okay? Because the description in the example is not telling you the sign of the power. So we translate that description into the sign. We should have P1 is positive 40, P2 is negative 50, and so on, so forth. So sum them up, we can come up with power of number 5 is positive 20 watt. Positive power means what? Absorbing, or say consuming. However, be careful, the problem we're asking is tricky, I have to admit. However, it's helping you understand the concept better. The question is asking how much power the element 5 supplying, not consuming. So how should we answer this? We should say 5 is supplying negative 20 watt, which is equivalent to consuming positive 20 watt. And also looking for the voltage across the 5. What we should notice is how to find the voltage. The power 20 watt positive is equals to V5 times I5. Right? I5 is given as negative 2 ampere, and also be careful the passive convention. The negative 2 ampere as it is entering into the positive polarity of the V5. Therefore, we just directly apply V5 times this negative 2 ampere. It equals to positive 20. Therefore, V5 equals negative 10. Now let's take a look at the example 3. Find the power by each element in the circuit A through D. So here we are seeing A through C, and the D circuit is on next page. So let's go over the circuit A here. We are seeing 3 elements along one single loop. Okay? And along this loop, you have one unique current, Ix, 4 ampere. So we can tell easily that each element here has the same current of 4 ampere. Let's see how to find the power for each one of them. So I'm using different subscript to differentiate different elements. For example, the power of 24 volts voltage source has power of P sub 24 volt, and it equals to the product between the current through it and the voltage across it. The current through this 24 volts voltage source is 4 ampere, as we said. However, you see this 4 ampere is entering the negative polarity of the voltage source. Doesn't match the passive sign convention. So here we can either flip the voltage polarity or flip the current direction. If we are flip the current direction, and then resulted current becomes negative 4 ampere, and the current entering the positive polarity of the source. And that way we can use negative 4 times the voltage 24 volts, ending up with a negative 96 watts. Negative power means supplying or delivering power. Second, the element 1 has voltage of 8 volts, and a 4 ampere current is entering the positive polarity of it, so matching the passive sign convention. We just directly apply 4 ampere times 8 volt, positive 32 watt absorbing power, or say consuming power. The third one, the dependent source. This dependent source is a voltage source due to the sign here, a polarity labeled. And this voltage source voltage value is depending on Ix, which is a current. So this dependent source is a current dependent voltage source with voltage value of 4 times 4, 16 volts. And the current through it is 4 ampere as well, entering the positive polarity in this loop. So we are using directly this 4 ampere times the voltage, 16 volts, ending up with 64 watt positive, absorbing the power. And if you verify these results by power conservation theorem, you will see sum them up, ending up with 0 watt. Perfect sense. Obviously, now you want to pause the video and try circuit B and C. And be careful in circuit B, the Ix is given as 2 ampere. And you have a current dependent current source in the middle. And apply the same idea we learned, you should end up with this solution. Okay. And to circuit C, you have a current dependent current source as well, with voltage labeled here. The trick of the circuit C is that Ix here is not given. However, and what can you do is by applying a power conservation theorem, you sum up all of the power together. It should be equal to 0. And each one of the power is in terms of Ix. So you can find Ix at the end and substitute this resolved Ix value back to each power and then to obtain the specified numbers. Okay, so please try them over and come back to check the solution yourself. And in the circuit D, last one, we basically follow the same idea to find each element's power by voltage times current and trying to match the passive sign convention. And the trick of this circuit is that we don't know the current of element 3, which is I0. It's something we don't know again. But what we can do is similar to circuit C. We apply the power conservation theorem and sum up all of the power together, and is equals to 0, from where you can find out the I0 value and substitute this value back to the P3. We can find the specified watts value. So just be careful also the dependent source. So this is a current dependent voltage source here. So exercise them yourself and then come back to check the solution and bring up the questions and concerns in the office hour.